Hello and welcome back to calculus. No, no calculus. Start again. Hello and welcome back to differential equations. Like I'm gonna edit this mistake. I'm not. So yes, differential equations, section 5.5 on multiple eigenvalue solutions, which is where you have that repeated eigenvalue. So what happens when you get lambda 1 equals 2, lambda 2 equals 2? Right, we did not have that case. We had the case when they're distinct, and we had the case when they're complex. So now we are talking about repeated eigenvalues, and we're going to take a look at, again, the same system we always had, which was this, right? And this is as you can see, the first order system. And for something like this, you want to have the distinct eigenvalues, which will give you distinct answers. So what we have done so far is we wrote that our solution was of the form C1 V1 e to the lambda 1 t. And then we had plus C2 V2 e to the lambda 2 t, where lambda 1 and lambda 2 were different values. Plus, and I'm just going to go like this and say, maybe you have 10 equations, right, which would make this into a 10 by 10 matrix, and you have 10 eigenvalues, and maybe all 10, right, 5 pairs of complex ones, right, so you can have all of that stuff. So Cn Vn e to the lambda n t. Now, this is a universal solution that fits the complex eigenvalues as well, except you would have complex numbers in the exponentials, which you can actually use Euler's equations to convert into the sine cosine equations we know and love. But all of the solutions are fit in there. Now, what happens if once you solve those solutions, you end up with repeated eigenvalue. So let's say, right, that your system that is given to you is x prime is equal to 9, 4, 0, -6, -1, 0, 6, 4, 3, and then x, right, vector. So what do we have? Well, we know to solve for lambdas, we find the determinant of 9 minus lambda 4, 0, -6, -1 minus lambda and 0, and then 6, 4, and 3 minus lambda, right, which will insert work here, which is the work from, before 5.2, and you know the work, right? Find the determinant, and you get something that is like this: 5 minus lambda, and you get 3 minus lambda squared, which gives you the multiplicity, gives you multiplicity of the root. So lambda is equal to 5, we call that M1 solution, and lambda 2 is equal to 3 multiplicity 2. So multiplicity meaning how many of the same root you have. So clearly it's a 3 by 3 case. You are expecting 3 eigenvalues, and there they are, 3 eigenvalues. You have 1 of these and 2 of these, so that's altogether 3 eigenvalues. 1 is 5 and 2 of them are 3 each. Now, we all know what to do for this one. That's solved by 5.2 method. There's nothing new there. So you will go and say when lambda 1 is equal to 5, right, you will solve the system of 4, 4, 0, -6, -6, 0, and the last one is 6, 4, and -2 times ABC is equal to 0, 0, 0, right? You see that these two equations are the same, which clearly gives you, right, A plus B equals to 0, right? Whether you're going to put 4a and 4b and divide by 4, you're going to put negative 6a, negative 6b, divide by negative 6, whatever. You get this equation, so a equals negative b, right? So let a, let's say, be 1, in which case b will be negative 1. And then you have the last equation of 6a plus 4b minus 2c equal to 0, from which you can calculate your c. So if a, that's going to be a 6 minus 4 is equal to 2c, so c will be 1, and you get your 1, negative 1, 1 eigenvector v1. So this is one of the possible eigenvectors. If you come up with 2, negative 2, 2, that's also okay, right? Any multiple of this vector will do. Now, what we are learning today, and I'll label this as new, is what happens when your lambda 2 is equal to 3 with the multiplicity 2, which means repeated eigenvalue. Right, so for repeated eigenvalue, we get to do the same system again. So when I plug everything into the matrix, I get 6, 4, 0. I get negative 6, negative 4, 0. And I get 6, 4, 0, A, B, C equal 0. Now I am going to say that this is the easy case. And I call it easy case because I want you to remember that this is the easy case because the problem one is coming up. Now, this is actually called complete in proper mathematical terminology. And as you can see, you are getting 3 equations that are the same. So 3 equations that are same. So you are getting your 6a plus 4b is equal to 0. And you are getting this across all 3 equations. So this can happen, right, if the system is what we say complete. And in this case, when you divide everything by 2, you get that 3a is equal to negative 2b, and then a is equal to negative 2/3 b. So if you let b equal to 1, then your a is negative 2/3. Now, for this system, you can pick literally anything for C. Could be 0, could be 1, could be 7, doesn't matter, right? So since all 3 equations are the same, you don't get this extra equation that came from the 3rd row, because that equation is the same now as all previous equations. So we don't have that extra equation to compute C. Since all 3 equations are the same, we can pick any value for C. So let it be 0. Or 1 or negative 7. I really don't care. And you are getting your vector V, right, to be negative 2/3, 1, and 0. Now, you can pick 7 if you want. It really doesn't matter. Okay. Now, how do we put our solution together in this case? Well, see, there is another vector that you can pick which would also work. So if we label this as a vector 2, there is also another vector that you can pick, which is literally anything as long as A and B are zeros, which is from the trivial case, because now C doesn't have to be a 0. C could be anything else, because A and B could be zeros as well. You see, we did not want a zero solution here to say A equals 0, B equals 0, because that would give a 0, 0, 0 solution, which we didn't like. But in this case, if I say for V3, let A equal B equal 0 and C be anything, let C equal 1, then you get your V3 vector to be 0, 0, 1. And there you have it, right? You have your three vectors with your solutions, right? So you can write your solution now, x of t, as c1 v1 e to the lambda 1 t plus c2 v2 e lambda 2 t plus c3 v3 e to the lambda 2 t. Remember that the lambdas are the same. And all you need to do now is just to plug all of these things in. So C1 and V1 was what? Where's my V1? There you go. 1, negative 1, 1. 1, negative 1, 1. E, was it a 5t? First lambda was 5, right? Yeah, and the second one is 3. Okay, cool. Plus C2, V2 was negative 2/3, 1, 0, e to the 2 lambda. 2 lambda. Eigenvalue was 3, right? Yeah, I can't keep track with all this stuff. 3t, and finally C3, 0, 0, 1, e, again 3t. And there's your solution. Now, this is when the system is easy, in quotation marks. Meaning, right, system is easy, meaning it's complete. You calculate two eigenvalues, and then you can just pick the third you calculate two eigenvectors, right, the standard way, and then you just pick a third eigenvector to be anything that has A and B to be 0 without C being a 0, because you don't want a trivial case. So we picked 1, but you could have picked, 7 or whatever other number. And there is a solution. So now you can go on top, right? Collect all the tops for the x1, and then go through the middle for x2s, and go to the bottom to get your x3. And you have all three of your solutions. So that's when the system is labeled as easy, right? Complete. Lock the doors. Defective solutions, right? Defective cases where the system is not complete. Defective. So what do I have as a defective system? Well, now I am going to come up with this, but I'm not going to have the opportunity to come up with pick whatever you want for the second value. So we have to do some witchcraft, right? If you remember, when we did this all the way back, I believe in chapter 2, when we had the repeated, or chapter 3, when we had those repeated r's, we had to write the solution as times t, right? Well, that's now making its way into the defective cases. So for the defective eigenvalue, we'll have a minus lambda I squared times v2 equals to the 0 vector, and such that, now we'll do the example so it will make more sense. I just have to write the algorithm down so we get that out of the way. V2 is equal to V1. There we go. So you're going to use obviously you're going to use the first vector to calculate the second vector. And then you'll have, so then the solution is x1 of t will be v1e lambda 1t. Guys, this is your 5.2 line. There's no difference there. But the new one is, and this is your new one. This is what we are studying now. x2 in that case will be v1t plus v2 on e to the lambda 2t. So that's the lambda 2 that was repeated. And as you can see, this one, right, goes to the both of these. So this was coming from the 3 by 3 case, let's say. Could be 2 by 2 as well. I don't need this stuff here. But the procedure is you will find your first eigenvector, eigenvalue, eigenvector pair, right? And you are going to have a V1. And then, as you can see, you are going to square your matrix, which is multiplied by itself, and then work it out for V2, but you will be setting it equal not to vectors of 0, 0, 0, 0, you will be setting it to the vector V1. Why am I not going through any of this theory? Because obviously I want you to take linear algebra, right? And understand there's no way I can teach you a chapter of linear algebra just so you can understand what the hell happened here, especially if you don't understand what eigenvalue and eigenvector mean at this point, right? That's another issue. Was that a question? Probably accidental. All right, so your first eigenvector will be computed the regular way. The second eigenvector will be, instead of setting it equal to 0, vector of zeros, you will be setting it equal to the first eigenvector. So let's go and try and figure out one of these problems, see what we get. So let's say you have your system of 1, -3, 3, and 7. There we go. So your matrix for lambdas is 1 minus lambda, -3, 3, 7 minus lambda. We need the determinant equal to 0. So that's going to give us 1, okay, fit here, 1 minus lambda times 7 minus lambda plus 9. And this works out to be 7 minus 8 lambda plus lambda squared plus 9, which gives us lambda squared minus 8 lambda plus 16, which factors into lambda minus 4 squared. And when you set that equal to 0, you get lambda is 4 with multiplicity 2. Awesome. So what I have here is lambda is 4, and multiplicity 2 means repeated eigenvalue. So now what I'm going to do is I'm going to say lambda equals to 4, and I have my matrix that's 3, -3, 3, and 3 and 3, right? Yes, 3 and 3. Okay, so what am I going to do now? Well, times AB is equal to 0, 0. Now, we have a problem over here, right? Because when you plug in the top, you get A minus B equal to 0. And for the bottom is A plus B equal to 0. And this can only happen, right, if A and B are both zeros. Because if you put any other values, right, the subtraction and addition of the two values is not going to give you the same number, not going to give you 0. So we can't solve it, right? So busted, right? So dead. So what do we do instead, right? Well, instead, we square the matrix. And that's in the procedure. If you are reading the formulas carefully and care about the procedures and stuff like that, you will immediately see that you are supposed to multiply the two matrices together. Now, matrix multiplication is well defined. We know what to do. We'll get another 2 by 2 matrix. So when we plug in this 3, 3 onto 3, negative 3, we're going to get a 0. Then when I put this on the first row, I get negative 3 times I'm not getting a 0. What's wrong over here? Something is wrong, guys. I'm supposed to get a 0 here, but I'm getting a negative 18, and that's not good. Something is wrong. Give me a second. So when that's a minus. It's 1 minus 4 is negative 3. I had the first value here. I had it backwards. I had it bad. Okay. So that's a negative there. That's a negative there. And now, okay, now I'm getting all zeros. Good. There we go. Awesome. Cool. So now we are getting that this matrix 0, 0, 0, 0, 0 times any choice of vector, right, would technically give us a 0 vector, which allows us to pick anything. So let me write that in blood over here. This equation allows us to pick any vector for V2. And you can pick 1, 0, 0, 1, 1, 1, 3, 7. I don't care what you pick, right? So if you pick V2 to be, let's say 1, 0, you can pick anything, right? Pick 1, 0, and then you go and you execute this. So I have my matrix, and then I hit that with this one, and that will give me V1, which is what? Negative 3 and 3. There we go. So I can write my solutions. X1 is V1. Now we're writing the solution from the procedure again. This. So V1 is V1 times, which is the vector, times e to the lambda, which is 4t. X2 solution is going to be V1, which is negative 3, 3, times t, plus the other vector that we picked 1, 0, all of that times e to the 4t. And now we know that the total solution is C1 negative 3, 3 e to the 4t plus C2. You can do this, negative 3t plus 1, and then just a 3t e to the 4t. What I did is I just added two column vectors, right? I distributed that t. This t is distributed to both negative 3 and 3. And then from the second one, I just added 1 and a 0. Obviously, 0 doesn't do anything. So here is the total solution to the case. Now I have my x1 going upper one. I have my x2 going on the bottom row. You know how to separate those two if you want to. And again, I'm being a terrible person. This is supposed to be x vector because it's x1 and x2 mushed in a single x value. So guys, I hope that you see that we used the process the way it's supposed to be processed, the way it's supposed to be used. I say that, oh, and now, by the way, this thing works because all you have is a plus b equal 0. I mean, the process still doesn't work, but it works differently now to show why it doesn't work. So both equations are now a plus b equal to 0, right? And the only way you can get them, because they need to be the same values, right, is to get the 0 is to a to b equal to negative b, but that will not, sorry, that would not work. So gone. Anyway, this is the procedure right here. More about this, obviously, either office hours or take the linear algebra course. But I don't know how to make this square more visible. There you go. So you saw me multiply matrix by itself, right? Solve the problem, picked anything, because I got all zeros everywhere, right? And previous example would not have that. You see over here, if you are to multiply these two, it's not going to work the same. So you have to be very, very careful, right? When you have a defective system, right, you do this. When you have a complete system, you use the previous one. How do you know? Yeah, that's what the homework and exercises are for. I can talk about it, I can demonstrate it, but I can't understand it or learn it for you. I can't practice it for you either. The fact that I'm solving problems and doing these things in class, I mean, you might as well make popcorn and have the same result, right? Which is not knowing anything after the fact. You watching passively, not taking notes and not repeating these problems on your own is not going to help you in your situation at all. So that's what's happening when when you have the repeated eigenvalues. And now you can just make this worse, right? Because you can have a triple repeat, in which case you have a t squared and so on, which makes this sound, we're not going into those, not just because this is not honors. Even honors doesn't go into it because this is introductory differential equations. This is like a scraping the surface, trying to uncover what's under, and then there is a whole glacier of things under, right? You should have like 5-6 different courses on differential equations if you are in a STEM, you know, and one of them minimum being a partial differential equations course. And you have dynamical systems, you have advanced differential equations, and then a whole bunch of other stuff with linear systems as well, dynamical systems and so on. It's a lot of differential equations courses. This is like 0.1% of stuff that it's out there is this entire course, including Laplace and everything else. In introductory course, we are only dealing with this very basic, very simple problem, right? And the procedure here is you square it, you come up with the values, you get your vector, and you pick your vector, right? If you get the matrix of zeros, you pick your vector, and you go through the calculation. So again, if you're ending up with these systems, let's solve another problem from homework just because we can. They don't even bother writing differential equations. They just put up a whole bunch of these. Oh, it's gonna be like almost all problems. If you flip the book and look at the homework, they're all 3x3 cases. So we have what, 15 minutes? Yeah, good luck. 14. Let's see if we get anywhere close to solving it. 0, 0, 1, -5, -1, -5. Please mentally get involved so that I'm not making silly mistakes, so we have to backtrack. That's a 5. That's a 5. All right. So subtract. There we go. Lambdas on the diagonal. So that's negative lambda 0, 1. -5, -1 minus lambda. -5. 4, 1, -2, negative lambda. And then, oops, we are supposed to do the determinant of this equal to 0. Now, determinant is you start with a negative lambda, and then you have your -1 minus lambda times -2 minus lambda plus 5. And then we have -0 times, we don't really care. And then you have plus 1 times -5 minus 4 times -1 minus lambda. So one more time. When I do the lambda, then I have the diagonal plus 5. That's good. For the second one, 0 times whatever, we don't care. And for the third one, it's 1 times -5 minus 4 times -1 minus lambda. Okay, so it looks good. But let's see when we multiply everything. So I have a negative lambda. Over here I have 2 plus lambda plus 2 lambda, that's plus 3 lambda, plus lambda squared plus 5 makes this into a 7. So I don't have like 15,000 steps. This is all gone. And then I have 4 minus 5 is -1 plus 4 lambda. Right, so that's a plus 4. So -5 plus 4 is -1. And then that's a positive lambda with a plus in front, positive lambda. Okay, good. That needs to be equal to 0. I get negative lambda cubed, -3 lambda squared, -7 lambda plus 4 lambda minus 1 equal to 0. And this gives me -3 lambda, and I just multiply the whole thing by a negative sign, so times -1. So we get lambda cubed plus 3 lambda squared plus 3 lambda plus 1 equal to 0. And would -1 be a solution here? That would be -1 plus 3 minus 3 plus 1. Yes, okay. So I just guessed that one. I mean, you can always go on a computer and factor it and so on, but we can also do this. So lambda equals -1, and that gives me lambda plus 1, a factor that I can... I put a new cooling. Why is this still twitching? Okay, let's see. So now I can divide lambda plus 1 into the whole. Lambda cubed plus 3 lambda. Oh, I can do the synthetic division. It's a linear. linear factors. So -1, and then I have 1, 3, 3, 1. So copy 1, that's a -1, that's a 2. That's a -2 gives me 1, and then -1 gives us the 0 at the end. So 1, 2, 1. So we have, it's a triple. So we have a lambda plus 1 times lambda squared plus 2 lambda plus 1 equal to 0. And this is just lambda plus 1 cubed equals 0. So lambda is -1 multiplicity 3. All right. So let's go and see what we have for this one. So what do I have for my lambda equals -1? What's my matrix? It's all the way up here. I'm just going to copy this mess. Copy. And bring it over here. And then fix it. So since lambda is -1, I know that I don't need this 0 anymore, right? And I know that I am going to use this. When lambda is -1, this becomes +1. -1, this becomes 0, right? And -1, this becomes -1. A, B, C equal to 0, 0, 0. All right, come on, tablet, you can do it. So if you take a look at the first two rows, I have the same equation, right? Because if I divide the second row by -5, I also get 1, 0, 1. So I have this A plus C equal to 0, and the third row is different. Now, third row being different, right, means that I can calculate B from there. So if I know that A is equal to -C and let C equal to 1, then A is -1. Or you can let A to be 1 and then C is -1. It doesn't really matter, right? What matters is that the third equation will give you the value for B. And we call this a complete system, right? Because the third equation was okay. Now remember, we still have the other two vectors that we need. Because again, 3 equations, that's x1, x2, x3, meaning we need to have 3 vectors. B from here, which is what we are looking for, is going to be C minus 4A, which is 1 plus 4 is 5, if I did this arithmetic correctly, which gives us first eigenvector of -151. And that takes care of things. Cool. Now what do we do? Now we square the matrix and see what we get from there. Now we have 1, 0, 1, -5, 0, -5, 4, 1, -1 times itself. It's going to take forever, but such is life. This goes on that. So 1 times 1, and we are going to get a 5 over here, because that's a 1, negative 5 dies because of the 0, and a 4, 1 plus 4 is 5. Then we move 1 over, and we get a 1. Then we move 1 over, that's a 5. My terrible handwriting, and it's very difficult now because the tablet is getting overheated. 1, 0, negative 1, so that's a 0 right there. Now we'll go to the second row with the first column. That's going to be negative 5 and negative 20, negative 25. And then 0, 0, so it's going to be a 5. And then the third one is going to give us negative 5, positive 5 is going to give us 0. And then the last row, you have to do 9 multiplications. That's 4 minus 5 minus 4 is negative 5. This one is just going to give us negative 1 here. And for the last one, we get 4, negative 5, plus 1, another 0. All right, good. Good shape, good shape. So there's my
A Professor?
Squared. Yes.
Shouldn't the most middle one be negative 5, not positive 5?
Okay, so if it's the most middle one, that has to be a middle one times middle one. So 0 kills the negative 5. Yes, correct. I didn't have the chance to check it. Yes. And yes, because now they're all the same equation. Right? Very good. Because now you see what you have is, okay. They're all now 5, 1. All of these equations, if you divide by negative 5 over here, and you divide by negative 1 over here, you get 5, 1 everywhere. All right, so now we have this 5, 1 creature, and that's going to give us a relationship between A and B. So 5A plus B equal to 0, and you pick B to be 1, and then, no, B is equal to negative 5A. B is equal to negative 5A. You pick A to be 1, then B is negative 5. I'm just trying to make it to be easy. And anything for C, any C, so C is equal to 1. C is equal to 0. How about that? C is equal to 0. Because we can't calculate C. They're all zeros there, right? And the procedure for that second, go away, procedure for that second vector, right, was to, well, we could have picked anything anyway. So V2 is 1, negative 5, and 0. 1, negative 5, and 0. This is A. It's just terrible. Yeah, I know the class ends in like 16 seconds, but let's get through this mess. So we have a V2, and now we need V3, and the V3 is that vector, because now, guys, if you take this matrix and multiply by itself, you're going to get the matrix of all zeros. And that's the matrix where you can pick anything to be your vector. So pick V3 to be 1, 0, 0. 1, 1. Anything that it's not linearly dependent to the two vectors that we already have. If you want to pick, each number to be, 3 halves, go ahead. So where are my vectors? -1, 5, and 1, 1, -5, and 0, and 1, 1, 0. So the solution all together, remember, now you have to have a t. So C1t C1 V1 plus C2 V2t plus C3 V3t squared, all of that e to the, what was my lambda? -1, negative t. It's a lot of mess. And now pick your vectors and you can separate them and do all of these things. So it's just a lot of writing. We know what the vectors v are. You just go back and plug them in if you want to. But it was a 3x3 case, and remember, all three eigenvalues were the same. Therefore, right, t and t squared. The previous one, we only had a single repeated eigenvalue, which means only this was present, because you only had multiplicity 2. Now you have multiplicity 3. For multiplicity 4, you have t cubed, right? And so it follows the same rules what you learned for repeated roots for characteristic equation back in chapter 3. There's no difference there. So there you have it. I will open the homework so you can enjoy this over the weekend. And I want to call chapter 5 here and say, okay, let's jump into chapter 6 and see what we have over there, because we just need to take a look at some stability and all of this stuff in chapter 6. I really need to get into chapter 7 as soon as possible. I was even thinking to go chapter 7 first, just to make sure that we know that, because that is the learning outcome of the course. And Laplace is what most of your professors will be using in your 400 level courses when you transfer out. Chemical, electrical, mechanical, I don't care which price. This is the favorite way to solve differential equations by far, and you will see why once we get there. I mean, we had some cool stuff already, right, where we didn't use any calculus to solve differential equations with those matrices and system and eigenvalues, like we didn't take derivatives or anything like that, or integrals. And Laplace is going to do the same, except you have to, have the values with it. So I'll do some thinking over the weekend, and then come Monday, we're either going to be in chapter 6 or chapter 7. We'll see how that goes. So see you guys on Monday.